Good morning, afternoon, or evening. Brin with Trained by Techs here. Super excited to be back with you today. We have a 2012 Ram 1500 5.7 liter. Little bit of an engine noise, rough running condition, P0303. What do you guys think it could be? I know many of you have experienced it firsthand, and if you haven't, you certainly have heard about it. Common issues with these Ram 5.7 liters is, of course, valve train problems. That's not what we're here for today. We could, of course, show you another case study with a valve train problem on something that you guys are probably already aware of. No, more or less, we want to share this one with you because it's pretty cool to the differences in symptoms, and when these symptoms occur. But also, it's pretty cool the differences in scope captures from one fault to another. So, of course, we're dealing with valve train issues on these Rams. Usually, it's going to be a cam lifter and/or a camshaft lobe that's worn on them, causing problems with either the intake or the exhaust side of a specific cylinder. In our case, the P0303, of course, we have a cylinder 3 specific misfire. So again, not so much about the actual fault on this vehicle because many of us have experienced it, have heard of it, but more so just when the symptoms occur and what the symptoms are from one fault to another, whether it's affecting the intake side or the exhaust side. The other part that's interesting is the different scope captures for whether it's an intake problem or a scope exhaust problem. For many of you that have decided to work through the learning curve that is, diagnosing engine mechanical problems using pressure transducers and scopes, and some of you have actually already worked through it, and some of you are working through the learning curve that is using these testing techniques. Of course, we always say you've got to get efficient on known good cars. But if you have a scenario where you have a known bad car, but you already have a pretty good idea of what is bad, then you can also use that to kind of help you understand how to perform these tests and what to expect to see. So we think it's a pretty interesting case for that reason, and hopefully you guys agree with us. Come on along with us, and we'll see if we can't learn some things. Take care. I don't know, man. This is
Bravo!
What about Bravo? No. So this are the fault codes that we have. Some of them are, most of them are self-induced, whether it be from the client or us. Electronic throttle control for sure. Ignition coil, secondary circuit insufficient, ionization. Those usually, in my experience, when you see those, at least when they're not self-induced, it's a legitimate concern with the ignition system, but they're certainly not going to really chase those at this point, knowing that there's most likely a problem with the engine mechanical. Cylinder 303, of course, and in the fuel injector circuits, I suspect the customer did say he tried just about everything. So he was already suspecting mechanical, just brought it to us to prove it. So I suspect those are self-induced as well. So this is just a screen capture of the scan data that we wanted to look at to try to get a direction here. Again, we had a pretty good idea of what we were dealing with, but it's always good to take a quick moment and look at the scan data. Before we go here, we generally will look at the misfire data, which we did. I don't know if I have a screenshot of it or not. But in the misfire data, what we found is, by the way, during our test drive, the symptoms weren't present at idle like they often are. It was more or less on light accelerations coming off of idle. But here we are kind of duplicating the symptoms, and but during the misfire side, we of course saw cylinder 3s counting misfires when we were able to duplicate the concern, or at least feel it more, and that's what, again, during light accelerations, whether it be brake torquing or actually accelerating from a stop in the parking lot here. But cylinder 3 would of course be on bank 1, and if you look at the O2 sensor, bank 1 sensor 1, it looks a little bit hashy, and it looks like it's trending on the high side. If you compare that to bank 2, where are you at? Where are you at? Well, there you are, right next to it. Bank 2 sensor, or upstream sensor, you can see it's kind of switching high and low more appropriately, and it's a little, I don't know if hashy is the right way of saying it, but it just looks like we would more expect to see, what we would expect to see more. And then the downstream sensor for bank 1, there's a little more activity on that sensor than there is on the bank 2 sensor. So what I'm trying to show here basically is if your scan tool is not giving you, if the misfire monitor is not running, if it's not giving you a misfire status, you can sometimes look at O2 sensor activity to get an idea of what bank it is at least, and then kind of go from there. So in our case, the long-term and short-term field trims on bank 1 were around 10 to 13% negative, where bank 2 is you're pretty good, way closer to 0. So again, more of an indicator that you definitely do have an issue on bank 1. And the negative field trim could be a hint as well as to what is going on. But let's go ahead and get some scope capture, since we already have pretty much planned on. All right, so the other thing we've talked about in the past is when you want to use your scope, it's kind of important to get yourself set up on like a diag card or something so that you can have it kind of ready. Otherwise, if it's sitting in a box or something somewhere, you're way less likely to get that thing out and start using it. So just wanted to take a quick moment. This is our mobile setup, because we do work in our own shop, but we also go to other shops with to try to help them diagnose cars. So this is our setup. Kind of just wanted to show you what we have going on here with the truck. Of course, when we have a suspect engine mechanical issue, we're going to use a high current clamp here and anywhere on the starter circuit, in which, obviously the part of the starter circuit includes the starter motor, the cables, the battery itself, the cables going to the starter, and then of course the ground coming back to the battery. So generally we'll put the current clamp on the negative cable coming back to the battery, because it's usually the easiest one to get a hold of. And just, with common fundamentals of electricity, you realize the current in that starter circuit is the same everywhere in that starter circuit. So that's the convenience, that's why we can conveniently locate that clamp there. So we're going to do a relative compression. I generally almost always get a sync. You can see here our blue cable is kind of hard to make out. It goes down to cylinder 1. I try to sync cylinder 1. Usually, if I will also put a pressure transducer. In this case, this is Mike Nicholson's Nicholson pulse sensor here. Very good sensor, very similar to a first look sensor or pressure pulse sensor. We have his sensor in the intake. Always got to use a centrally located port. I usually go for the purge vacuum port on the intake, because of course it's got to be centrally located. And we also have a pressure transducer in the suspect cylinder here. That's cylinder 3, of course. And when you're doing this, you're going to want to, when you're doing cranking, and so when you're going in cylinder, you want to do cranking and running, and then oftentimes snap throttle as well. I usually see what I need to see in the cranking and running captures, but you have to check the suspect cylinder, but you of course have to check the a known good cylinder, so you can compare and see the difference between the two. That's the beauty of having only having to diagnose a single cylinder misfire or single cylinder mechanical fault. But yeah, that's what we have set up. Now, you wouldn't necessarily normally put all of these or use all of these channels the first time you're scoping, but in this case we know we have a pretty good idea what we're going after, so we went ahead and just took the time to set it up, which is, of course, after you've done this a few times, it's not terribly time consuming. It takes a few minutes to set this stuff up. So we've got it set up. Let's go ahead and we'll go ahead and get our relative compression capture with sync and see what we can come up with. There's one more thing I wanted to mention about doing relative compression captures when you're trying to monitor intake pressure as well, which is a beautiful combination, and it's very easy to set up. One thing I wanted to mention is when you're doing 4 and 6 cylinders engines, it's usually the trace is pretty clean, it's not a problem, but when you get into 8-cylinder engines, the intake pressure trace can get kind of messy, be kind of hard to really use to analyze a scope capture. So what I do is I actually unplug the throttle body, so that I think part of the problem is during cranking, the ECM or PCM will try to open and close that throttle, and it just makes analyzing the intake pressure waveform basically not conclusive, and it can be difficult. So of course, The problem is if you unplug it, if your vehicle is a vehicle that supports clear flood mode, which of course when you're doing relative compression you have to keep the engine from running so that you can crank it over and monitor the starter current to determine relative compression. But if you unplug the throttle body, then it's not going to go into clear flood mode because it's not able to monitor the TPS sensors because they're unplugged. So you would leave that plugged in, and you can't close this all the way, but I usually find a way to close it off mostly. Now this is not necessarily super ideal, but if you have it positioned in a way that it allows a little bit of air into the throttle body, but this throttle blade itself opening and closing a little bit will affect the waveform less than normal. So that's kind of what I do, and just something to think about. All right, so we're going to walk you through how to set up the scope. In my case, I usually go with the ignition sync on the first channel or channel A, and because I'm using a 4423 with a maximum voltage of input voltage of 100 volts, I will use an attenuator, which is this guy, and put it on the B and C connector and then put your test lead to that. Basically, we've discussed this before, that reduces the actual voltage. In this case it's a 20-to-1, so it reduces it 20 times. But by choosing times 20 here, I'm telling the scope to multiply the input signal 20 times, so it actually displays what the actual circuit is doing. So I've done that. Now I'm going to choose my settings. I usually choose 400 volts when I'm dealing with primary ignition. For those of you who don't know, of course, most cars out there are coil unplug. If it's a 2-wire coil unplug, it's going to be, primary is going to be accessible. If it's 3+ wires, 3 wires, it may or may not be accessible. If it's 4+ wires, generally it's not going to be available, so you're going to look at just a ignition trigger or sync. In our case, we can see primary voltage, so I'm just going to do that. So usually I'll use channel B for my actual starter current for the relative compression. In our case, we're using a 2000 amp clamp, and we're going to need to use it in 2000 amp mode because most likely during the relative compression it's going to take more than 200 amps to turn this engine over for every cylinder. So we use the 2 to 500 amp. Of course, you're not going to it's going to clip the top of the waveform for the initial starter inrush will go beyond 500, but we're not worried about that. We're just looking for the consistent relative compression starter current during the, as it needed to turn each piston over through the top dead center compression stroke. So now in this case we'll use C, we'll go ×1 because that's going to be our Nicholson pressure sensor in the intake, and I will probably put it, anywhere, I'd say 2 to 5 volts to start, and we can always change it. And obviously with the beauty of picoscope we can do vertical enhancements too here if we need to. But D's where our pressure transducer in cylinder is going to be, which is going to be the WPS 500 range 1, because in range 1 is where we're going to be able to get the pressure needed for cranking and running compression. Of course, those of you that are familiar with WPS 500, it's 3 pressure transducers in one, and you can choose one of 3 different ranges, and range 1 is the one we need for cranking and running compression. When we're cranking, it's going to oftentimes, they're going to go over 200 psi, so I will choose the highest range here during the cranking compression. So, of course, when you're doing relative compression, the WPS, by the way, self-calibrates. You just have to push, turn it on and wait a few seconds for it to run through the self-calibration. And then, but when you're using a current clamp, in this case, you would turn it on, and then you would simply hit the 0 button. And once you hit the 0 button, then it'll go in through its like self-calibrating mode and 0 out as well. So that's how we would set it up. I usually choose, 1 to 2. I shouldn't say. No, I usually do 200 milliseconds per division and 1 to 2 million samples per second. You don't need anything crazy sample-wise. So that's what I'll do when I do the relative compression capture or running capture. I'll use pretty much the same setup, and just the only difference is when I'm going running compression, it's going to be generally below 200 psi in cylinder, so I'll choose the 100 psi usually. But during the these things you can change if needed. So that's how we're going to set it up. We'll go ahead and do our relative compression capture now. Now, I mentioned a moment ago clear flood mode. Most of you probably know, but if you don't know, clear flood mode is a scenario where the vehicle will allow you to just crank the vehicle over. It'll basically, the control module will disable the fuel injectors so that the engine can be cranked over. The idea is if it is flooded, you can just open the throttle and stop fuel flow into the cylinders and eventually clear the flood. So the way you would do that on a vehicle that supports it, which I generally try every vehicle before I have, because you're doing relative compression, you have to obviously disable the engine from starting, which means shutting off the fuel pump or figuring out a way to shut off the injectors, which you can do with a scan tool sometimes. You can do it by physically unplugging them, or sometimes if you're lucky there's a fuse. But on a vehicle where you can do clear flood mode, where you just simply depress the throttle to the floor while you crank it, it will automatically do it, and that's a beautiful thing. So here we go. Now, the thing about relative compression is, old school folks really understood this before you even started using scopes to test this. They just understood that you had to pay attention to the cranking cadence. If there was an issue with the cranking cadence, like you could kind of suspect at that point there's certainly going to be a compression difference from one cylinder to another. Well, keep in mind there's all kinds of valve train problems that don't necessarily show up in cranking compression. So as you can tell from just now, we didn't have a difference in cranking cadence. It was pretty smooth. Each cylinder sounded like it was contributing equally, mechanically speaking. So, well, let's take a look at the capture and see what we came up with. All right, so here's the results of our relative compression capture. This is cylinder 1's ignition sync. So of course, starter current increases as the piston reaches top dead center. So each time you see this red trace, which is starter current toward a peak, that represents top dead center. In this case, that's the sync cylinder 1 ignition trigger. So that's top dead center for cylinder 1. So firing order is 1, 8, 4, 3, 6, 5, 7, 2, back to 1. We said that when we were cranking it, the cranking cadence sounded even, so we didn't expect to really see a difference, really, relatively speaking, cylinder mechanical contribution from one to another. Of course, 1, 8, 4, 3, 6, 1, 8, 4, 3, this one being 3, pretty even with the rest of them. So the green trace here is the intake manifold pressure, and how we are able to determine which intake pool is which. Let me go ahead and pull up an annotated capture of it. So again, starter current representing relative compression, 1, 8, 4, 3, 6, 5, 7, 2. Well, when it comes to intake pressure, each time a piston descends in the cylinder with the intake valve open, that piston is pulling on the intake manifold. And each time one of these pistons descends during the intake stroke, you'll see the pressure drop in the intake manifold. So in this case, we have a Nicholson's pressure sensor or pressure differential sensor in the intake manifold, and we're seeing the pressure change in the intake manifold. How do we determine which pull is for what cylinder? It's pretty easy if you think about how the 4 strokes work. And if I go back to the regular capture and we move our rulers down to 4, so we can just see it as the 4 different strokes, this is cylinder 1. So cylinder 1, top dead center compression, now moving to bottom dead center during our expansion or power stroke. Then piston goes back up on the exhaust stroke, back down on the intake stroke, back up on the compression stroke. So this right here is the intake stroke. So just to the right of center is going to be your intake stroke on your synced ignition synced event. So now if we go back to the other capture, that's how we're to determine which intake pool is for what cylinder. Cylinder 1, just to the right of 360 degrees, just to the right of center, that's when the intake stroke starts for cylinder 1. So this is the cylinder 1's intake stroke or intake pool. So then we just plot our firing order, 1, 8, 4, 3. Well, if you look, we're looking for anomalies, right? That's what we generally do when we're scoping, is we're looking for repeatable anomalies. And if I were to back out, which I probably can here, if I back out on this one, close this out, you'll see that that anomaly continues, repeats. So let's go back to our annotated waveform here. You see this anomaly here, and it does repeat. And that anomaly happens during the intake pull of our suspect cylinder. That's interesting. Why are we having that rapid and deep pull? That's twice as deep as the rest. Generally speaking, you wouldn't expect to see a deep pull on the suspect cylinder's intake stroke. So let's figure out why. All right, so normally I would just do a nice screen capture voiceover video here so that it would be easier on the eyes, but unfortunately I just don't have the time to do that, so I'm just going to, hope you don't mind, I'm just going to show you the screen. This is a cranking compression for the known suspect cylinder 3 cylinder. So I've gone over this, we've gone over it, there's a lot of information out there, but of course each one of these peaks represents top dead center compression. So when you mark your rulers here at each top dead center compression, that's 720 degrees, or the full four strokes of that cylinder. This of course is compression, back down to expansion, exhaust, back down to intake, and then back to compression. So what we're seeing here during cranking, usually I'll show you a known good cylinder here, which again, that's what you generally try to do, is go to known good, because even when you see, get familiar with what known good should look like, every engine's a little different. So it doesn't mean, if you see something weird, it doesn't mean it's wrong. So you compare it to another known good cylinder on the engine. Let me bring the cursors back down here. The rulers, partitions I should say, to 4. I'll leave that up. So you can see that this a little anomaly here is not there on the known good cylinder, and it is there on the known bad cylinder. One thing I wanted to bring up is, the relative compression showed that the compression was about the same. You can see here this one's 236.4. If we look at the known good, 235, so very close. What happens though around the 360 degree mark is the end of the exhaust stroke and the beginning of the intake stroke. So the exhaust valve will start to close at about 360, but the intake valve will generally open right around that point. And there usually is some slight overlap. But if you see, generally speaking, now again you have to compare to known good, but generally speaking on a cranking waveform, as you can see from the known good, you won't have this anomaly. You have very little detail in this whole section of the trace. As you can see on this known bad, you see this dip right here. Well, the piston is coming down from top dead center. That intake valve should be open. But if the intake valve is not open, you're going to pull the cylinder into a negative pressure, and that's what's happening. So you'll see here at this point where I've put this cursor, that's about the time the intake valve must have opened and then the pressure equalized, which, at this point it's cranking compression, so when the intake valve opens, you're reading the pressure in the intake manifold here during the intake stroke, and the pressure in the intake manifold when cranking is pretty close to atmosphere. So that's why you don't have a lot of variance or detail in cranking compression waveforms. So right away we can see the intake valve is probably opening late on this suspect bad cylinder. And if we look at the next part of the trace, here's the compression stroke here, and at this point the piston is coming up toward top dead center from bottom dead center. As the intake valve closes, pressure starts to build. Well, usually the faults on these rams are some kind of lifter or cam lobe fault where you have excessive lash. So when you have excessive lash, and it has excessive lash because the lifter and the cam lobe generally wear. So it has excessive lash, so when you have excessive lash, your valve will open late, but it'll close early. That's just the way it works. So the intake valve is closing early in this case. If we were to move this over to the point where we can see the pressure start to rise confidently right around there, and then we move the cursor, the other cursor, to bottom dead center, and you can see the difference is about 37 degrees. And if we go to the known good capture, let's see, our cursors are way over here, sorry. Put it at bottom dead center. Oh, you know what? Our cursors aren't properly marked, so let's move them. There. And if we move this to bottom dead center, and then the other cursor close to where we think the pressure starts to rise confidently, we're looking about 40, 45 degrees there. And again, if we look at the known bad one, about 37 degrees maybe. So, and maybe even a little sooner. If we were to zoom in here, we can see it's probably starting to rise probably right around there, which gives us 25 degrees. Let's go back. We can't go back. Let me take this. It's the problem with looking at, let's go back to the known good, and we'll do the same. Pico's awesome, but their software does get a little glitchy sometimes. I'd say probably right about there. So you have 42 degrees versus, what was it on the other one, about 25 degrees. Yeah, so 25 versus 42, but a little over 15, 17 degrees difference. So the intake valve is closing about 15 to 17 degrees early on the known bad capture, but it's opening late. So they kind of counteract each other, is what I suspect is why we have pretty equal cranking compression. But if we look at running compression, oh man, that's a bummer. I'll have to open it up. Shoot. I can open up the known good, I believe. There's the known good. For those of you that are familiar with these captures, turn the other channel off. That looks pretty textbook. There's not a lot odd going on there. So this is the known bad or suspect cylinder. As you can see, the deepest part of the intake pool is kind of late after bottom dead center here. That's because the intake valve is opening late, and then it starts to ramp up very early in the compression stroke here, which is again an indicative of the intake valve closing early. The other thing that's pretty interesting is you'll see this deep pull, and then it kind of comes back up a little bit, and that's indicative of like a valve that's partially restricted or not opening enough. So intake valve is opening late, closing early, and we're seeing evidence that the intake valve is not opening enough. So shorter duration and lower lift all points to excessive lash issue, which on this vehicle we probably, or as indicated early on, we knew it was most likely an issue with the lifter and or cam lobe, which was probably going to cause excessive lash, which causes our noise. But that's the other thing I want to get to here is the symptoms in just a moment. So this little small point here was just to kind of show what to expect when you have excessive lash on an intake trace. If we go back, we had a kind of a question a moment ago on the, let's take another look here. We'll add our partitions up back to 8, and we'll kind of zoom in a little tighter. No, that's not what we need. We'll zoom in a little tighter. Why are we getting this anomaly? Well, what's happening is normally the intake valve opens really close to that top dead center, the 360 degree mark, which would be, the intake valve normally opens very close to here. What's happening is your piston is going from, it's ascending or going up in the cylinder, and then going from going up to going down. So it's at its slowest right here. The intake valve generally opens at that point, and the pressure is pretty equalized. The cylinder pressure is pretty low. If the intake valve opens late in the intake stroke, then there's already, the pressure in that cylinder is already pretty negative. Much more negative than it would be if the intake valve opened early. So because the intake valve is opening late, the piston is already on its way down a good ways in the cylinder. The pressure is negative, so when the intake valve does actually open, you get this rapid and deep pull on the intake stroke on the suspect cylinder. Because again, that valve's not opening early in the stroke. When the pressure is equalized, it's opening late in the stroke when there's a negative pressure in that cylinder. Once that intake valve opens, now all of that, that's going to be pulling rapidly the intake volume into the cylinder, and that's why you get that deep fall. So just kind of interesting. If it were the other way around, if you were to have an exhaust valve, not, excessive lash on the exhaust valve, you would have a totally different signature. Let's see if I have can show that. Now this is from a 2011, so this is from 1 year older model that we had a while back, and this is the relative compression capture. Relative compression looked pretty good on that one. This had an exhaust valve issue, excessive exhaust valve lash due to a worn lifter and cam lobe. And what you'll see on that type of failure is this. Instead of seeing a deep pull like we see in ours because of a late intake valve opening, you see a rapid rise in intake manifold pressure when the intake valve opens on the suspect cylinder. And the reason for that is if the exhaust valve is not opening enough and closing too early, there's still some contents left in that suspect cylinder at the end of the exhaust stroke. When that intake valve opens, now all of that volume that's trapped in that cylinder now gets pushed back into the intake manifold, is why you see this rapid rise in intake pressure when the intake valve opens on the suspect cylinder. So just a different waveform, totally different waveform, whether or not you have a exhaust valve issue or an intake valve issue, which I think is pretty cool. Well, appreciate you guys bearing with me. I realized that this is a long video, but I thought that, I feel like there were some teaching moments I wanted to make sure that we shared, and and because I'm long-winded. Sorry guys, I'll work on it. I'll keep working on it, I promise. But what's pretty interesting is, depending on whether you have an intake valve or exhaust valve issue, the symptoms are, at least when the symptoms occur, different. Obviously you're going to have a cylinder misfire, rough running condition, cylinder misfire code. But if it's an exhaust valve issue, generally speaking on these anyways, because it's usually a worn lifter and or cam lobe, basically excessive lash, so the valves open late, they close early, and probably the lift itself is lower. So lower valve lift and lower duration. If it's on the exhaust valve that's affected, then you will have, the contents won't be expelled after the combustion. So the volume that's trapped in the cylinder will now get pushed back into the intake, creates kind of like an EGR effect for that single cylinder, which causes a rough running condition at idle. Now if it's an intake issue, you're not going to really feel it at idle or see misfires count up. And that's because, I guess it depends on the severity of the fault, but because the intake valve is still opening, it's opening enough and long enough to keep the engine running smooth at idle. But where you'll see it is during acceleration. In our case, it was a light to moderate acceleration. You could see the misfires count and kind of feel it more. And the reason for that is the intake valve opens enough during idle so it doesn't necessarily affect the way it runs. But when you go to accelerate and open that throttle, and now all of the cylinders need equal amount of volume coming in, but you're kind of restricting the intake flow to that one cylinder, so you'll see evidence of it during acceleration. So again, the biggest thing for us is necessarily what the fault is. Most of us are going to know right away, based off our experiences or somebody else's, what's probably causing the issue. But it's just kind of cool to see the different scope captures and how they look depending on whether it's an intake failure or exhaust failure, but also focus on what kind of symptoms you would expect from one versus the other. Keep in mind, this is only because this is a common fault that we're able to kind of differentiate the two, but also the severity of the fault does come into play as well. So anyways, thank you guys so much for hanging out with us. Again, sorry for the long-winded video, but thought it was pretty cool. Hopefully you guys enjoyed it. If you like what you see, please subscribe. Let us know if there's anything that you'd like to see, and we'll try to work on it. Also, please leave your questions, concerns, or comments below. That's where the conversations begin, and we all learn from each other, and then, of course, we're all in this together. So thank you again for your time and attention, and hope you guys have a great day. Today's Halloween, so have a great Halloween if you're watching this.